n to get this. All right. Now, earlier we mentioned that it was a sort of an accidental phenomenon that you got this redundancy, and the cause of that energy eigenfunction redundancy was due to the nature of the potential, because it was a Coulomb potential of the form some constant divided by r, and hence you got these degenerate energy eigenfunctions. All right. Well, when you start bringing this stuff in, then your potential is no longer Coulomb. So when you move outside the Coulomb realm, so your potential now is no longer Coulomb. When that's the case, well then the degeneracy disappears, and then the energy will depend on the angle, the theta and pi, and so forth. So this degeneracy will then disappear. So when your angular momentum L here is non-zero, positive, right? Then you get the degeneracy disappears, and so you'll have then a one-to-one mapping between the eigenvalue and the eigenfunction. Right? That's what non-degeneracy is. Okay. So in other words, for each energy level, there'll be corresponding energy eigenstate, and since the eigenstates will be different, right? Because we're talking now non-degeneracy, therefore the energy eigenvalues must be slightly different, right? Now it's a fairly small. There's fairly small effects. Oh, that's what I was looking. I was looking for this term. Yeah. So in other words, because of these these smallish effects, you'll get a change in the values of the eigenvalues for energy. So these are the energies values we get, En, that we've done earlier, earlier sessions. And you'll get these corrections, if you like, these small adjustments, if you like, delta, delta, small changes in the energies due to these kind of phenomena. And next chapter, we'll do some of that. And when we get into heavy quantum field theory in M1 and M2 levels, this so-called subtle tiny effects from QFT, you'll appreciate the size of these deltas, right? But I must say, when physicists, quantum mechanics, people make statements like quantum mechanics is the most accurate theory that humanity has ever devised, because it's due to these QFT, quantum field theory type phenomena, where these delta E's are very small, but measuring the size of these delta E's became fantastically accurate, like 1 part in 10 billion. And it was that fantastic accuracy, this between the theory, quantum field theory, and the extremely accurate experimental measurements, and the match between the extremely accurate experimental measurement values and the predicted, the theoretical value due to phenomena occurring in quantum field theory. But you'll have to wait a year or two before studying that. But that match was so spectacular, 1 part in 10 billion, that it convinced in the 50s, I think, 40s, 50s, that quantum field theory was legitimate. Because it really only got going in the 40s, right? There are 4 main guys. 4. Yeah. And the big star of those 4 was Dick Feynman. And at first quantum field theory was all exotic and not understood and new, but once it started making these fabulously accurate predictions compared to experimental results, people really began to believe in it. Okay, so next chapter we'll talk about, well, particularly part B, coupling with spin, for example, and orbital angular momentum and whatnot. So next chapter, quite a bit of theory as well. And we're heading, there are only 11 chapters in the book, so next chapter will be chapter 9, so expect it to be a bit harder as well, right? Okay, now I still have a bit of space left, so just as I did several sessions ago, I thought I'd introduce some more books. Now, they are all by Greiner. As you know, I love Greiner, the author, a German physicist, who's written a whole series of textbooks originally in German for German students. And I love their thoroughness and their sheer competence. The Germans, in general, are the smartest people in Western Europe, together with the Dutch, but the Dutch genetically are Germans in a sense. I mean, have you ever thought about the connection between the word Dutch and Deutsch? Right? Dutch is just the dialect word for Deutsch, and Deutsch is the German word for German. Ich bin Deutsch, ich bin Deutscher, I'm a German. I'm not, I'm just saying that. But so, the Dutch and the Germans, they're the smartest on average, highest average IQ in Western Europe, 105, equal to the Northeast Asians at also 105, Chinese, Koreans, Japanese. Okay, so I very much like the sheer competence and thoroughness. Germans are known for being thorough. So are the Japanese, both superb engineers. And thoroughness and attention to detail is a very useful quality for engineers. So it's not surprising the Japanese and the Germans are superb engineers. Right? The rest of Europe's going down the tubes with their debt problems, but Germany's export industry is doing very well. And I can see why, because in China, where I live, I see luxury cars, BMWs, just all over the place here. So the German export industry from their car industry is doing very well. Okay, so German competence, Greiner's competence and thoroughness, I really appreciate. So I will use 3 of his books in future quantum mechanics type courses. I'll say it in German because I speak German. Ich habe ganz gern, I really like, die deutsche Gründlichkeit, German thoroughness. And you'll see, when I get into these textbooks, these Greiner textbooks, you'll see what I mean. Very thorough, every point covered, and competent. You will, if you keep following me, you'll love this stuff. All right. So the 3 texts themselves. Each one will be a course, a graduate level course. Quantum electrodynamics, or QED, is let's see, that would be an M1 level, like a later M1 level course. You'll need to have done quantum mechanics M1 first. I've shown you the book for that. It was one of the Mandel books, a green one, green covered. And so once you've done master's level M1 quantum mechanics, then you can do quantum electrodynamics. So that's later M1 level. Now gauge, the theory of weak interactions. The basic theory of this is modelled on this. So the techniques, Feynman diagrams and so forth. If you've never heard of I'll just say it. Feynman, that's Dick Feynman, famous physicist, one of the best in the 20th century, American theoretical physicist. He created a technique to visualize, using diagrams, the mathematics of the interaction of electrons and magnetic fields and electric fields and so forth. Anyway, so those techniques got used to explain the weak interaction. It's the weak nuclear interaction, responsible for, say, beta decay and the decay of the neutron, stuff like that, right? And then these two fields got wedded, they got merged, and now you talk about the electro-weak